Hello everyone, I'm Ziyao, a PhD student from Shiyuan University, China. Today I'll present to you my work towards building condition-based cross-modality intention-aware human-AI cooperation under VR environment. This work is completed in cooperation with Mr. Shiyuan Li, Dr. Yunpeng Song, and Professor Zhongmin from Shiyuan University. VR applications are increasingly incorporating AI assistants, enabling users to interact and cooperate with virtual agents in immersive spaces. To achieve effective cooperation, it is crucial to accurately understand users' intentions from various input modalities and tailor the presentation of information to support decision-making. However, three key challenges must be addressed. The first one is user expression ambiguity. Users may express their intentions ambiguously, relying on implicit knowledge or intuitive assumptions. For example, they might say, "items that fit in my car's trunk," without specifying the car model or size constraints. Additionally, VR allows users to leverage multiple input modalities such as speech, gaze, and gestures, making it difficult to infer their needs based on a single modality or fixed rules, such as the one I'm looking at. The second one is AI recognition and recommendation inaccuracy. AI assistants must accurately recognize user need and provide relevant recommendations or responses. However, the quality of prompts used in large language models can significantly impact recommendation accuracy, potentially leading to incorrect or non-existent suggestions. The last one is generating and adjusting tailored responses. VR environments offer a variety of output modalities from various visual cues such as highlight, pop-ups, to voice responses. To provide optimal assistance, AI responses should be tailored to the user's specific needs and expressed through a combination and coordination of appropriate modalities which many works might overlook. In response to current challenges, research on human-AI cooperation in VR is rapidly advancing. Some researchers develop algorithms combining various modalities like eye tracking and gestures to discern user intent, relying on data and algorithmic design. To enhance response generation, efforts focus on crafting multi-modal responses catering to the user's search goals, attention levels, emotional state, etc. Also, chatbots are increasingly integrated into VR for immersive experiences during scenarios like counseling and shopping. Nowadays, in light of the widespread adoption of large language models, can these efforts be unified under a single framework to achieve coordination through LLM? LLM may reduce algorithm training requirements, understand some of the user's implicit assumptions, guide response generation with its programming language generation capabilities, and they obviously align well with language-based interactions that chatbot needs. Our goal is to address these challenges and enhance human-AI cooperation effectively with the power of LLM in VR. To this end, our work centered around designing a condition-based cross-modal human-AI cooperation framework as the following. This framework centered around constructing intent, condition, intent prompt, action prompt tuples as the intent library. Here, intent signifies the current user intent category, and condition represents the task attributes that map to the corresponding intent. The intent prompt serves the purpose of classifying the intent and corresponding condition, while action prompt consequently directs the systems in generating a series of actions to execute. In this process, there are two LLMs involved in the cooperation. The first one is the intent LLM. It utilizes the user logs and the collections of intent and corresponding intent prompt from the intent library. And then it is capable of detecting user intents based on the user's multi-modal behaviors through matching intent tuples in the intent library. Based on the detected intent and corresponding conditions, the system could then perform filtering and retrieve the relevant results, such as the products from the merchandise library. The second involved LLM is the action LLM. Based on the user logs and the retrieved results, the action LLM realizes the condition-based user intentions and corresponding action prompt from the intent library to generate various action orders, such as float labels, voice responses, highlights, etc. In such a framework, AI assistant in the system can effectively utilize the user's multimodal data to first detect the user's intent and then efficiently filter the actions to be executed based on the condition, thus leading to subsequent efficient action generation. Our work is carried out in a VR virtual shopping environment, so I will take a shopping case to briefly explain our framework. Suppose the user sees two shelves and asks the following question: which is taller, these two shelves? Then the user's intent should correspond to compare because he needs to compare the values of two products in the same attribute, height. Therefore, condition is the product that needs to be compared, shelf A and B. What needs to be compared is the height, the maximum value. So, according to our framework, the process of our system should look like this. The user's voice input and eye movements are combined and passed to the intent LLM to be recognized as compare intent with these conditions. Then, after querying shelf A is higher, the action LLM generates a series of actions. Specifically, in our system, this includes the voice reply of shelf A being higher, the adjustment of the float label relating to user attention, here is the height, and the right arrow above shelf A as an indicator. Here I give a portion of what the actual prompt in the example contains for illustration. In our article, we define 8 kinds of intents for shopping scenarios in total, including get info, get product, compare, refine, disambiguate, add to cart, unclear condition, and chat. These intents, coupled with corresponding conditions, could help the system in assisting users better expressing their shopping intention, locating users' accurate intention and focused conditions through intent LLM, and guiding the response generation tailored to the user's needs and interests through the action LLM for better human-AI cooperation shopping, as well as responding to users' Q&As that require daily knowledge. Next, in order to investigate the effectiveness of our design framework and intent library, we propose the following 3 research questions. The first one is, does condition-based cooperation compared to cooperation lacking such mechanism lead to improved efficiency? The second is, what impact does condition-based cooperation have on various human-AI interaction behaviors? The third question is, do users perceive effective assistance in the condition-based cooperation system? What are their subjective attitudes? In our user test, we developed a VR virtual shopping system as follows. The system features over 140 models of real furniture organized by category along corridors. Users interact with an AI voice assistant supported by a 2 LLM architecture we designed, powered by GPT 3.5 Turbo for intent detection and action generation. Users need to complete shopping tasks, interact with furniture in the scene, compare options, and cooperate with the AI assistant to obtain a shopping list matching the tasks. As users focus on one piece of specific furniture, relevant float labels will display illustrating their current focused conditions. Users could also click on items to reveal detailed product pages. Users can add products to their cart through clicks or AI assistants. After selection, users need to review their cart, potentially submitting multiple times until all items are correct. We devised 2 comparing systems to evaluate our main system's efficacy. In System 2, we eliminated the condition-based propagation mechanism. Float labels are no longer provided based on user focus. Instead, the AI assistant directly processes user speech and all product information for recommendations. System 3 lacks a voice assistant, retaining only product details upon user interaction, serving as a primitive blank control. Here are some experimental results and conclusions we've obtained. Comparing time and efficiency, we found that condition-based human-AI cooperation significantly reduces time and submission counts, aiding users in finding expected products faster with fewer errors. We also evaluated LLM's performance, noting that condition-based human-AI cooperation fosters efficient multimodal conversations and enhances LLM's appropriateness in responses. Furthermore, examining user behavior, we observed improvements in LLM intent recognition and users' interaction tendencies with AI. Users also become more proactive in utilizing information from various modalities in our main system. Lastly, regarding subjective attitudes, users reported higher satisfaction and perceived efficiency within our main system. Drawing from our experimental findings analysis, several noteworthy implications arise. Our approach of decoupling intent recognition from action generation effectively filters products, significantly reducing the prompt length for LLM processing, thus aligning more closely with human needs. The intent library we devised categorizes user abstract behaviors, achieving commendable intent recognition within GPT's token limit. Future iterations could follow such example and expand this library by incorporating other user intentions of other tasks. Moreover, our 2 LLM architecture aptly constrains large language model outputs, enhancing controllability and result accuracy in task-oriented settings. While our study focuses on shopping scenarios, we argue that our framework's applicability extends beyond, as illustrated by our discussion on deploying AI assistants in space stations, underscoring its versatility for future investigations. Here's the review of our work. More interesting details and some explanations could be found in our paper. I encourage the audience interested to read our paper and don't hesitate to contact us. Thank you all for listening.